Hello everyone. Today we are going to discuss about curl of a vector field. So here we will discuss about this particular terminology. What is curl? Vector field, everyone is aware of what is vector field, right? Initially in another video, I explained you what are the fields and what are the types of fields and all. So curl of a vector field. Till now we discussed about this del operator that we discussed, which is given by I cap del by del x plus j cap del by del y plus k cap del by del z, which is a vector differential operator, right? Can be operated on any scalar del phi that will give you the maximum space rate of change of that scalar function, right? Del phi, okay, or grad phi that we discussed. Then we discussed about the divergence. Divergence when this operator is operated on a vector with a dot, right? Then it will give you the net flux emerging out per unit volume, the physical significance we discussed. Now here we are going to discuss about curl of a vector field, and that is when the del operator will be operated over a vector field by cross, okay, with the cross operation, cross product. Okay, let us see in some more detail, okay, what is this del cross A. Mathematically, first we will try to understand, and then we will see what is the physical significance of it. So cross product of any two vectors, okay, here this del is nothing but a vector operator, right? It's a differential operator, vector differential operator. Let us now revisit to the cross product of any two vectors, okay? Suppose I will say this is vector A and this is another vector which is B, right? And if you want to find out what is A cross B, the rule is simple and we know that in terms of magnitude, if I'll write, then this vector, the magnitude of vector A, magnitude of vector B, and then sine of the angle between them. If it is theta, then I will write sine theta. Okay, and then n cap. This n cap actually gives you the direction of this vector A cross B, right? So if you are rotating A towards B like this, okay, then what will be the angle, right? And if you are moving B cross A, then what will happen? A cross B, you can see this is in clockwise direction. So clockwise direction, so right hand screw rule can be used or right hand thumb rule can be used, right? So when it goes, clockwise, you are rotating the screw in clockwise direction, then you are actually tightening it, right? The screw will go down, right? The screw will go down. So this will be the direction. This cross means what? This is a vector which is perpendicular to this plane but going inward, right? Now if I'll do the same thing but for B cross A, okay, suppose here I will say this the same vector, pair of vectors I have taken, vector B and this is vector A. The angle is the same theta here, okay, and now you're finding B cross A, right? So if I will take B cross A, then the magnitude will remain the same. You got B vector and then magnitude of A vector, sine of the angle between them, and now n cap. Now this n cap will be what? B cross A, you are moving counterclockwise. That means you are loosening the screw actually, right? You are opening the screw. So it will come up. So a dot means it is perpendicular to the screen, perpendicular to the plane that we are considering on which A and B lies. Okay. The same rule that we will use for del cross A or curl of a vector field. So as it follows the cross product, we are going to follow the same thing. Similarly, one more thing I can say where, this A cross B you wrote in a matrix form. So you wrote it as, if you remember, I cap, J cap, K cap, okay, these unit vectors along three mutually perpendicular axes. Then you have the component of x, ax, ay, and az. These are the x, y, and z components of the vector A. Similarly, bx, by, and bz, right? These are the components of vector b in all three uh, axes, right? So this is what we said a cross b. Now the same thing we will use when we will determine curl of a vector field. So let us see mathematically what we will write for curl of a vector field. Then we will see the physical significance. So you have to be very particular about the direction of this vector when you are multiplying two vectors with a cross, right? So here when the differential operator will be operated on a vector, it will also be a vector quantity, and the direction will also be given by what? The same right hand screw rule or the right hand thumb rule. Okay, so as you can see here, okay, so here the curl of the finger, you can see the curl of your finger represents the direction of rotation, right? Whether the vector, I mean, in what direction the vector is actually rotating, right? Clockwise or counterclockwise. Here you can see it is moving counterclockwise. In case of a screw also, you can see the same thing. If you are rotating it counterclockwise, it will open, right? So you can see it's going upward, right? So the thumb represents the direction, that rotation, right? Similarly, if you see the curl represents here, you can see if the curl is just opposite, right? Just like, here you can see the curl is like this, clockwise, okay? Then the thumb will represent the direction which is downward here, okay? So this is the product rule, sorry, cross product rule, and the same thing we will use while explaining del cross A. So let us now find out what is del cross A mathematically, then we will see what is the physical significance of this del cross A actually, what it actually gives you. So if I will write it mathematically, del cross A, let us substitute all the values. So first the del operator, I cap del by del x plus j cap del by del y plus k cap del by del z, right? This is our del operator. You can see it is in a vector form cross the vector A, which is I cap ax plus j cap ay plus k cap az, right? This is the vector. So in the determinant form, if you want to write, then you can write it as I cap, j cap, k cap, right? And then you have del by del x, okay, del by del y. These are the x, y, and z components of the del operator. Del by del z, the partial differentiations. Okay, then you have this ax, ay, and az, the components of the vector a, right? So that way we can write. Now you know how to expand this one. So if you are taking this I cap, then you need to take this, let me use some other color here. So you can see, if I'm considering I cap, then you take the difference between these two multiplied, right? Then minus j cap, if you will take, then the same way you can take this, okay? Like del az by del x minus del by del z of ax, or if you are taking it plus, just take the reverse. So whatever way you want to write, you can write it, okay? So I'm just expanding it. Okay, let us expand it and then we will see. I cap, this one I kept. Okay, so I got in my bracket what del a z divided by, sorry, del az by del y, not divided, is the differentiation. So del ay divided by del z, this is what we got from the I cap. Then here you can write minus j cap or plus j cap, accordingly your order will change in the bracket. I'm writing plus j cap just to keep it simple. Del ax del z minus del az by del x, right? The j component we got, or the y component, and the k cap we can write it as del ay by del x minus del ax by del y. So you expanded it, okay? So k cap, if you take this diagonal, like ijk and this, then you got del ay by del x minus del ax by del y. So this way we can expand. Now here one thing we need to see, that this I cap, j cap, k cap, they are the unit vectors associated along x direction, y direction, and z direction. So here, if you will see any of these variables exist, what do you mean by that? In the first bracket, if you will see, in the first bracket, if you will see this thing, right? That means what? If your del Az by del y or your del Ay by del z are non-zero, then this I component will exist. Similarly, your del Ax by del z, okay, and del Az by del x are non-zero, and j cap component will exist. Similarly for k cap. So what do you mean by this? When I let us just see the first thing, the first term here that we got mathematically. Actually, what it says, I cap, we got del Az by del y minus del Ay by del z. That means what? If this Az, which is the z component of the vector, okay, z component of the vector, okay, that is z component of the vector a, and its variation with respect to y, that means del by del y of this z component of the vector, which we said is z, okay, this is suppose non-zero. Non-zero means what? This az component is a function of y. Similarly, if del by del z of ay is non-zero, okay, then what do you, and the second thing is they are not equal, then what you will see, this component will, this whole thing will be non-zero and this will exist. The same is applicable for all other terms for j cap or k cap respectively. Now what it says actually, what do you mean by this? If I said del cross a, that gives you actually how the vector field is rotated. So del cross a actually gives you what? That's why we are using a cross product over here, how the vector field is rotated. And the vector field will rotate, okay, and you will get a non-zero value only if this z component will depend upon y component will depend upon z, and they must not be equal. If they will be equal, then you got this zero. The same is applicable for j cap and k cap as well. So x component must be a function of z, then only this term will exist. Z component must be a function of x here, x component must be a function of z, then this will exist and this should not be equal. Same with k cap. That means what? We got the variation of all these components, x with respect to y, then x with respect to z, and then similarly y with respect to x and z with respect to your x and y. So all these components should be, should have some value, or overall this bracketed term that we showed here, these bracketed terms should exist, right? This should not be zero. I mean, you can say one of the component is zero, but not all three, right? Then we can find out actually what del cross A will exist. Del cross A will exist. When you say del cross A exists, that means the vector A has a rotating effect. Okay, so curl of a vector actually gives you the rotating or rotating effect of this vector field A, right? And how to find out that? This you need to just determine this del cross A and just check whether it is zero or not zero, right? If it is zero, if it is zero, that means what you got? Zero means you must get zero over here, you must get zero for this term, and you must get zero for this term. That means there is no rotating effect of the vector field, right? It's not rotating. But if you get non-zero, if it is non-zero, then the curl exists. Okay, and if the curl of a vector field is zero, then we call it actually irrotational vector. Irrotational because it doesn't rotate, there is no rotational effect. Irrotational vector. Okay, so mathematically, this is what it represents. Del cross A, you got the rotating effect of a vector field at any point in space, right? So every field actually is a function of position and time, right? So now if there is a change in the coordinates in the xyz value anywhere, right? If the vector field is moving or the scalar field is moving, right? you need to find out the change, right? So the change can be determined for a vector field by two different ways. One is by applying del operator with a dot product, which will give you the net flux emerging out per unit volume, and the other is by applying the del operator with a cross product, okay, which we said as curl of a vector field, and this will give you whether there is a rotational effect or not, okay. So rotational effect or not, or there is the whether there is net circulation of the field or not. So that is what it will give you. So mathematically, I hope you understood this, the representation of this curl of a vector field. Now let us see the physical significance of the curl of a vector field. So what is the physical significance of curl of a vector field? So, okay, now we can say the curl of a vector field is a vector, okay, which will represent the net circulation of the field, okay, or we said the rotating effect of the field, okay. The magnitude of the vector represents the maximum circulation and the direction, okay. The magnitude of the vector which we determine there, okay, from that determinant, okay, that will give us the maximum circulation, okay, and the direction that is normal to the surface upon which the circulation is greatest. What do you mean by that? So from the cross product, we said that the resultant vector a cross b will always be perpendicular to the plane having a vector and b vector. The same way here with the right hand screw rule, or you said the right hand thumb rule is applicable there to determine. Same way here we can find out del cross a. So the vector here del cross a is nothing but in what direction actually the vector field rotates. So if it rotates in this direction, in clockwise direction, you use the thumb rule, and your curl of the finger will be in this direction, so thumb will point downward to this plane, okay. If it is counterclockwise like this, then your curl of the finger will point to this direction, and your thumb will point upward. So here you got downward and here you got upward, right? The vector. So this is the direction of curl of a vector field. Right now you can see this a small animation that I made here. Suppose you think this way, that the water is flowing here, okay, in a stream, and then you can see these two sticks, okay. For example, these are the two sticks, okay, you can consider. So these two sticks, actually you can see how they rotate at a certain point, right? When they rotate at a certain point, you can see there must be a axis of rotation, through which, I mean, from which actually it started rotating, right? So here we can see how it rotates. That means the vector field has an effect of turning there, right? That's why the object you can see which is floating is at that particular point experiencing like a torque, okay. So it's rotating, right? So here you can see that the either you say the force vector, or you said the velocity vector has a turning effect, or has a rotational effect at a particular point, okay. And this is what is actually curl, okay. So we need to understand this physical significance of the curl of a vector field. So if I want to find out what is that turning effect there, okay, and what is the direction of the curl of the vector field, I can find it out by just operating this del on the vector field at that point, okay. So that will give me the curl of a vector, curl of that vector, okay. Or you can just see this particular, the same thing actually I tried to show. Suppose the vector field here is moving in this direction, this is the variation you can see, and you can see the object that was floating like a stick or something like that, okay, with respect to some certain point here, okay, it's rotating, right? So that rotational effect, now if you'll see what is the direction of the del cross a, it will be this point, like this perpendicular to this point, right? That will be your del cross a, right? And if your del cross a is not equal to 0, then the curl effect exists, right? That the rotational effect of the field, okay, exists. And if the curl doesn't exist, that means there is no rotational effect, there is no rotational effect. Right now when we said when the curl will exist, actually when the curl will exist, Okay, you saw that in mathematically we wrote, del a z by del y minus del ay by del z, right, plus j cap. This is I'm writing for call del cross a, which we just discussed. Okay, j cap del ax by del z minus del az by del x plus k cap del y by del x minus del ex by del y. So you take this function, like, you write this vector a, whatever the vector a is. Suppose I'm just randomly writing it like I cap 2x z plus j cap 3y square x plus k cap, some 4x z, something like this. I'm just randomly writing. Then you just take these values over here. Here your this value is your actually the x component. This value will be your the y a y component, and this value will be your az component. Then you substitute over here, okay, in this place, right? And then you see whether the curl exists or not. Okay, the curl exists or not. If the curl exists, okay, if the curl exists, then there will be a rotational effect of the vector field. If the curl doesn't exist, there will be no rotational effect. Okay, no rotational effect. For example, let us take position vector r vector. Okay, r vector, position vector can be written as I cap x plus j cap y plus k cap z. Okay, what is position vector? You all know that. I'm just showing it in 2 dimension. It can be extended to 3 dimension. Suppose here, so this is your position vector, you said, right? Can be written as a function of, here you can write this as I cap x plus j cap y. Similarly, for 3 dimension, we can add this k cap z, right? Let us use this call vector, call operator on this r. What we will get? Okay, if I'll write this way, I cap del ax by del az by del y. So what is our az here? Az is your z, right? So you got del z by del y minus del ay, which is y, right? You got del y by del z, right? Then you got j cap. Okay, the same way you can write ax. So del x by del z minus del z by del x. Similarly, plus k cap. Here you got del ay means del y by del x minus del ax means x by del y. Right? This is what you got. So now these z and y, they're all independent of each other. They are all independent of each other. So each term actually vanishes here. So you got 0, 0. This is also 0. This is also 0. So what we finally got, del cross r is 0. So del cross r is 0 means what? Position vector is always directed straight, right? It doesn't have any rotational effect. It doesn't have any rotational effect. So now who will decide whether the vector field will have a rotational effect or not? The function itself, the vector function itself. So now what is the function, and then on that function you operate del with a cross product and then see the rotational effect of you can determine the rotational effect of that vector field. Okay, at any point when I said you just determine this, these values. Okay, and then find the del cross a value over here from the function, and then in terms of xyz as a function of xyz, of course I cap j cap k cap will be there. Okay, because it's a vector. And then you will get in terms of xyz, and then substitute the value of like whatever xyz, suppose 1 2 3 point, and then you find out, you determine del cross a. If it gives you a non-zero value, then at that point the call exists, and you can find out the magnitude there and the direction of the vector as well. If it doesn't exist, that means it doesn't have any rotational effect. If I'll substitute this point 1 2 3 in xyz, and after that I got del cross a is 0, then at that particular point there is no rotational effect. I can conclude that way, right? I hope you understood the physical significance and the mathematical explanation given over here. If you have any query, you can write it in the comment. Okay, so the curl operation is restricted to how the field changes as one moves across the field and is non-zero when the field increases or decreases. Okay, in a different direction other than that of the field. Okay, so this is how we can conclude. So if the field changes in the same direction as pointed by the field, the curl will be zero. So this is what we said. So mathematically you understood what del cross A not equal to 0 will give and del cross A equal to 0 will give. And then also we discussed one example of irrotational vector. When the curl of the vector field actually vanishes, we will call it as irrotational. The same way for divergence, if the divergence of a vector field vanishes, like for example, let me just write it over here, del dot A becomes 0, then we will call this vector A as solenoidal. Like we said irrotational there, here we will call it as solenoidal vector. Okay, solenoidal vector. Okay, so this is it in this video. Thank you for watching.